Swayam Prabha. Digital India. Educated India.
Welcome to the third lecture. Now we will start talking about piezoelectric materials. Now to understand these piezoelectric materials or piezoelectricity, we need to first understand crystalline and polycrystalline materials and some of the concepts of symmetry. Crystalline materials are materials where atoms have highly ordered, periodical, repeating arrangement. For example, if we see here, we can see that if we just take maybe this unit, we can see that this unit keeps repeating. So, if we go in this direction, if I go down below, if I go diagonally, I can see this pattern keeps repeating. So, it is a crystalline material. At the other end of it is a amorphous material. In amorphous material, there is no periodic pattern. So, we can see it here. We cannot define something which repeats here. Polycrystalline materials is something which can be thought to be in between these two, because here in a global sense there is no repeating pattern, but within each domain we can see that there is something which repeats. For example, here we can see that this cell keeps repeating, same thing we can see here. But if I compare these two domains or these two domains, we can see that the orientations are different. So, within each domain these units have their own orientation, and that remains consistent, but in two domains the orientations may not match. So, that is why it is called a polycrystalline material. Now comes symmetry. So, we have three elements of symmetry. One is plane of symmetry, axis of symmetry and center of symmetry. Now, plane of symmetry is if an imaginary plane can divide the crystal into two parts which are mirror images of each other, then we call it a plane of symmetry. For example, if we have something like this, if we think of one plane here, so this plane at the middle divides it into two halves, and these two halves are mirror image of each other. Similarly, we can draw another plane here also and divide it into two equal parts. So, these are all planes of symmetry, and these are generally called rectangular planes of symmetry. Now, there can be, for the same cube we can think of a plane like this which goes diagonally, and that also divides it into two parts which are mirror image of each other. So, that becomes a diagonal plane of symmetry. Similarly, there can be axis of symmetry. So, it is an imaginary axis about which if the object is rotated, its appearance is repeated more than once. Now, something which does not have an axis of symmetry, it needs to be rotated by 360 degree for the same shape to come. So, that is why we do not consider that, but where it appears more than once, then we can say that it has an axis of symmetry. So, in 360 degree rotation, if the appearance comes n times, then it calls an n fold symmetry. Which means the appearance occurs after a rotation of 360 degree by n. For example, here we have something called two-fold axis or dyad. So, here the appearance comes after 180 degree rotation. Now, to understand this, let us name them. Maybe we can call it 1, 2, 3, 4, 5, 6, 7 and 8. So, if it rotates by an angle 180 degree, let us imagine that these are the hidden lines. So, what is visible to us is this line 1, 2, 3, 4, this face 1, 2, 3, 4. So, if it rotates by an angle 180 degree, then what we can see here is this. So, we have after rotation the phase that comes is 7, 6, 5, 8 and 3, 2, 1, 4. So, the other phase 5, 6, 7, 8 that comes in the front and 1, 2, 3, 4 goes back, which means this shape again reappears. So, it is a two-fold axis of symmetry. In three-fold axis, the axis connects this corner with this corner. So, if it is rotated at angle 120 degree, again the same phase comes. If you want to understand it, let us again name it 1, 2, 3, 4 and let us assume that these two lines are hidden lines. So, we see the 1, 2, 3, 4 phase from the front, and then we have 5, 6, 7, 8. So, if it rotates by an angle 120 degree, then what we see is this. In that case, this phase which is 3, 7, 8, 4 that comes here, and accordingly the other points take place. So, after 120 degree rotation, the shape again comes back. So, that is why it is a three-fold axis or triad. Four-fold axis, it is easy to visualize. If it is just given a 90 degree rotation, this phase comes here and that is a four-fold axis or triad. And then six-fold axis, again if it is given a 60 degree rotation, this phase comes here and accordingly the other phase takes their shape. So, the shape repeats at an angle after a rotation of angle 60 degree. So, it is a six-fold axis or hexad. Now, we will talk about center of symmetry. Now, center of symmetry, if there is a point inside, the line drawn through which touches the surface of the crystal at equal distance in two opposite directions, then that point is called the center of symmetry. Again, if I take the example of this of a cube, so let us imagine that let us imagine the coordinates to be 0, 0, 0, 1, 0, 0 and we have 1, 1, 0, we have 0, 1, 0 here and then we have 1, 1, 1 1 0 1 0 0 1 and we have 0 1 1. Now, let us imagine one point at the center P, and P suppose it is half. So, if I draw a line, vertical line through P, it touches the top surface here and it touches the bottom surface here. Now, the distance of this point from P is same as distance at this points from P. Similarly, if I draw a line here, horizontal line, it touches the right face, here and it touches the left face here, and again the distance of this point from P and this point from P is same. We can do the same thing through diagonals also. If I draw a line from this and from here, again it touches the two corners at two equal distance. So, the point P is center of symmetry for this object and only one center of symmetry can exist. Now, we will talk about symmetry operations. So, symmetry operations are something which after being carried out leaves the object looking same, and there are various types of symmetry operations. The first one is translation symmetry. So, let us imagine that we have objects like this. It can be in 3D. So, we are drawing it in 2D for the sake of easiness. So, let us assume that we have a 2D array kind of structure. It can go in this direction, it can go in this direction, it can go. Now, here the distance between these two successive objects are same. So, it is all say A, it is all A. So, they are not changing, although in the drawing it may not be accurate and look little different, but they are all same. Similarly, in the vertical dimension, let us say they are all B. Now, if I take a point here and if I look around, so it says it is point 1. So, if I take a point here and if I look around, so whatever I see, if I take a point here also and if I look around, I would see the same thing also. Or in other words, if I take this point and replace and put it here, the look does not change. So, after translation it remains invariant, but here we have to understand that this translation has to be at a distance which is integer multiple of this A and B. So, if you are shifting towards this axis, the horizontal axis, it has to go A, 2A, 3A like that. In the vertical direction, it has to go B, 2B, 3B like that. So, if I do that kind of translation, it looks same. So, that is why it is called a translation symmetry. Reflection symmetry, a plane or line that divides the crystal into two equal parts which are mirror image of each other. Again we can look into this circle, we can see that we have a line here that divides the circle into two equal parts, not just equal, I mean similarly looking parts which are mirror image of each other, and it also divides it into two mirror image, and we can think of lot of axes, I mean infinite number of axes for this circle which can divide it into two equal parts. Rotation symmetry. So, here the rotation by an angle theta gives the same crystal. We have already seen that there is axis of symmetry with respect to which we rotate, we get the same shape back. So, if we do that operation, we get we do a rotational symmetry operation. Then inversion symmetry, again if for every lattice point at R there exists a lattice point minus R, and it is applicable to 3D only. We have also seen this. Now, there is something called roto inversion. Roto inversion means if the object comes back after a rotation and a inversion, then we can call it a roto inversion. For example, Let us imagine this. Let us imagine that we have one atom here and here, and they are same. So, if this is rotated by an angle 360 degree, it comes back here. If this is rotated by an angle 360 degree, it comes back here. So, we are doing a one-fold rotation to both, and then if they interchange their points. So, the center is somewhere here. So, with respect to this, if this point comes here and this point goes here, which means they interchange their point, I mean their locations, these 2 points interchange their locations, then what we get is point 2 here and point 1 here, and even then it looks same. So, after a rotation by 360 degree and then inversion, we get the same shape back. So, it is a one fold rotation with inversion. So, we denote it by 1 bar. Now, point to note is that here we rotated it this by 360 degree, which means that is not a proper rotation, because it is not needed actually. We without even rotating also, we could have just interchanged the place and get it. Now comes two-fold symmetry with two-fold roto inversion, that means two-fold rotation with inversion. To understand this, let us imagine a situation like this. Suppose we have an atom here and we have something here, but these two are different. So, that is why they are, one is solid, one is hollow, and then we have 3 here and we have then we have it here 4. Now, if they interchange their place, then 4 will go here, 1 will come here, which means the shape does not remain same. So, what has to be done here is, before doing the inversion, it has to be rotated. So, if it is rotated by an angle 180 degree, then 2 comes here and 1 goes here, and similarly, if the bottom part is also rotated by 180 degree, then 3 comes here and 4 comes here. Now, if they interchange their location, so which can be seen here, then what we see is 3 sitting here and 4 sitting here, and we see 1 coming here and 2 coming here, which means again we get our previous shape back. So, it is possible through one rotation, 180 degree rotation and then one inversion. So, two-fold rotation with one inversion. Now, point to be noted is, if would have reflected, then also you would have seen the same thing. So, if we put a plane here, maybe, and with respect to this we can see that these two are mirror image of these two, which means we could have avoided the rotation and inversion just by doing the reflection also. So, it is equivalent to reflection. Now, here the plane of rotation is the vertical axis and the plane of reflection is the horizontal. The plane of reflection is horizontal, which means the plane of reflection is perpendicular to the axis of rotation. Now, we will talk about a three-fold roto inversion. So, let us again imagine 3 points. Now, we will think of. One, 2, 3, and then we have 4, 5, 6, 4, 5, 6. Now, to get this shape back, what needs to be done is they all need to be rotated by an angle 360 degree. So, first of all we can see that they all are oriented at an angle 60 degree. So, this they all are 60 degree, and same here also they all are oriented. So, the angle between, so that these two successive points they make an angle of 60 degree. Now, if we do a one-fold rotation, if we do a rotation by an angle 60 degree, then what happens is our point 1 comes here, point 2 comes here, and point 3 comes here. And then here what we see is point 4 comes here, point 5 comes here, and point 6 comes here. Now, if they are rotated and if the places are interchanged, then we will see that point 1 comes to this point, and then point 2 comes here, and point 3 comes here, and point 6 comes here, and point 5 comes here, and point 4 comes here. So, the shape is back. So, that is a three-fold rotation with inversion. Now, we will talk about a six-fold rotation with inversion. Okay. Now, we will talk about six-fold rotation with inversion. So, let us imagine a situation like this. We have the atoms arranged in this fashion. And two successive atoms make an angle of 30 degree at the center here. Again we can see that if we rotate it by an angle 30 degree and then we invert it, then it becomes we get the same shape. So, if we rotate it by an angle 30 degree, so six-fold rotation plus inversion we can see here. And also we can visualize it in other way. So, we can, instead of doing a 3-fold rotation, if we do a instead of doing a 6-fold rotation, if we do a 3-fold rotation and then we reflect it, then also we get the same shape back. So, it is equivalent to a 3-fold rotation and inversion. Based on the symmetries, various point groups can be defined for crystals. Here we will talk about a point group in 2D. So, in 2 dimension there are 10 point groups, and these are denoted by these circles, dots and lines. The first one is 1, it is denoted by this circle with this 1 dot. Now, to get this configuration back, this circle needs to be rotated by an angle 360 degree. So, it is a 1-fold rotation. So, that is why it is 1. Here we can see this configuration, again to get this back it needs to be rotated by an angle 180 degree. So, it is just 2, and in both the cases there are no reflections. So, I cannot define any line with respect to which the two parts can become mirror image of each other. So, that is why I do not have any M here. Here we have both 1 and M. 1 because to get it back again I need to rotate by 360 degree. So, it is 1, and this line forms a, this if I draw a line here, that forms a mirror, because with respect to which is with respect to this line the two parts become mirror image of each other. So, it is 1 M. Here we have 2 mm, 2 because if we give 180 degree rotation the configuration comes back. So, it is 2-fold rotation, and there are 2 types of mirrors. If I draw a line here, that means if I put a mirror here, it become we get 2 mirror images. So, this part is mirror image of this part is mirror image of this. Similarly, this line also divides it into 2 halves which are mirror images of each other. So, it is 2 mm. Here we have 4 because after 90 degree rotation we get this configuration back, but there is no reflection symmetry here. So, it is 4. This is 4 mm because after 90 degree rotation the configuration comes back, and there are 2 types of mirrors. So, if I draw a line here and if I draw a line here, there are same types of mirror, because the mirror images that we get by this line is similar to the mirror images that we get by this line. But if we draw a line here and if we draw a line here, that creates different types of mirror images. So, although there are total 4 number of mirrors, the types are 2. So, it is 4 mm. So, it is not the number of mirrors, it is the mirror types that matters. So, it is 4 mm. Then comes 3. If we rotate it by 120 degree, the configuration comes back, but there is no mirror. So, it is 3. Here if we rotate by 60 degree, the configuration comes back. So, it is 6, there is no mirror. This is 3 m because if we rotate it by 60 degree 120 degree, the configuration comes back. So, it is 3, and here we have one with respect to this line we get mirror image, with respect to this line we get mirror image, with respect to this line we get mirror image, but all these mirrors are similar of same type. So, it is 3 m. Here we have 6 because if we rotate it by 60 degree we get the configuration back. So, it is 6, and this line create one type of mirror image. So, there is mirror of one type, and if I draw a line here or line through this or a line through this, that creates another type of mirror. So, there are 2 types of mirrors. So, it is 6 mm. Now, we will move to 3D crystals. So, there are generally 7 types of 3D crystals. One is simple cubic, as the name says it is a cube. So, A, B, C, all the lengths are same and all the angles are 90 degree here. Tetragonal, its A and B are same, but the vertical axis C is different and all the angles are 90 degree. Then comes orthorhombic, here all the I mean all the sides are different, A, B, C, they are not same, but all the angles are 90 degree. Rhombohedral, all the axis length, I mean all the sides are same, but two of the angles, I mean 3 of the angles are, none of the angles are 90 degree. And then comes monoclinic. In monoclinic, A, none of the sides are same, 2 of the angles are 90 degree and the other one is not 90 degree. Triclinic, none of the lengths are same and none of the angles are 90 degree. In hexagonal, we can see that A and B, they are same, but C is different and there is one angle which is 120 degree. So, these are all 3D different crystals. Now, in the next class, we will look into the 3D point groups and then from there we will see how piezoelectricity comes into picture. Thank you.